Hey everyone, so this is lesson number 8 on graphing reciprocal trig functions. And so just to refresh, when we're looking at graphing a reciprocal function, so let's say this is our function f of x, we're graphing 1 over f of x. There's a couple different things we need to look for. Any x-intercepts in f of x are vertical asymptotes in the reciprocal function. So at x equals -1, here we're going to have a vertical asymptote. X equals 1. And x equals 2. If f of x equals plus or minus 1, then at those same spots, our reciprocal also equals plus or minus 1. The reciprocal of 1 or -1 is the same. So we're going to cross through this point, -1, -1, and -1 again. Then from there, if we're positive, we stay positive. And same thing for negative, the reciprocal is negative. So we get a shape that looks like this. And remember, all reciprocal functions are going to have a horizontal asymptote at y equals 0. This point here, 1.5, the reciprocal, 1 over 1.5, we're going to be at about 2 over 3. Oh. This is at a half, so the reciprocal is going to end up at 2. And we get a shape that looks like this. So we're going to use this idea of reciprocal functions to graph cosecant of x, which is the inverse of sine of x. So first we'll start off by refreshing what the function sine of x looks like. So we start off at the origin, the point 0, 0. Sine of pi over 6 is 1/2. Sine of pi over 2 is 1. Sine of 5 pi over 6. So we have the reference angle pi over 6. We're in the S quadrant, the top left quadrant, so we're still positive. So it's still 1/2. Sine of pi is 0. 7 pi over 6 is -1/2. 3 pi over 2 is -1. -1 over 2, and back to 0. So we get this familiar sine shape. Cosecant is all the inverse of these sine points. So the inverse of 0 is undefined, which means we have a vertical asymptote at x equals 0. The inverse of 1 over 2 is 2. Inverse of 1 is still 1. Again, the inverse of 1 over 2 is 2. And then we're back to another point where we're going to be undefined. We're going to have another vertical asymptote at x equals pi. Going to have a shape like this. Now the inverse of negative 1 over pi is going to be negative 2. 1 over negative 1 is negative 1. 1 over negative 1/2 is negative 2. And we get another vertical asymptote at x equals 2 pi. So we can plug these points in. So this is going to be, in the blue, this is our function f of x equals cosecant x. So we can see it follows the same guidelines as the reciprocal functions we've looked at so far. Every time we added a 0 on our original function, we have a vertical asymptote on our reciprocal. The points f of x equals 1 and f of x equals negative 1 stay the same. And we're positive and increasing, so we're positive and decreasing in our reciprocal, and then positive and decreasing, positive increasing in our reciprocal, and so on. So we'll look at some of the key features we have in this cosecant function. So we can see we have vertical asymptotes every pi. This is going to continue. We're going to have another one at 3 pi, another one at 4 pi. So we can write that by saying we have a vertical asymptote at n pi, where n has to be an integer. The period of this function, we're going to repeat this pattern of this kind of parabolic shape going up, parabolic shape going down, every 2 pi. So we still have a period of 2 pi, similar to the sine function. Our domain, x is an element of all real numbers except where we have these asymptotes. So x cannot equal n pi when n is an element of the integers. And our range, we're only greater than 1 or less than negative 1. In between, there were no values from negative 1 to 1. So y is an element of all real numbers, such that y is greater than or equal to 1, and y is less than or equal to negative 1. And we can combine this together and say negative 1 is greater than or equal to y, and y is greater than or equal to 1. So this is a slightly different way of writing this. We're used to always writing this compound inequality using less than or equal to signs, but this is telling us that we have to be less than negative 1 and greater than 1. There's no x-intercepts at all in this function, and there's no y-intercepts in this function. We are never crossing either of our axes. So now we'll look at graphing our secant function. So just a reminder, secant is 1 over cos of x. We'll look at our cosine function to start. So our cosine function has a y-intercept at 1. Then it spends a full cycle on its way down, crossing a half at pi over 3. At pi, it's at -1. Back to the x-axis at 3 pi over 2. Then finally back up to 2 pi. So we get this shape here. And we'll look at the reciprocal now. So for secant, or any reciprocal, we're going to have asymptotes where we had x-intercepts in our original function. So we're going to get a vertical asymptote at pi over 2 and 3 pi over 2. And then points where we're at positive or -1 are going to stay the same. These x equals halves are going to become x equal 2. And -half is going to become -2. And we can complete our shape. The rough sketch. Oh, that should go up that way. And we have our secant function shape, which looks an awful lot like the cosecant, just shifted slightly. So we have a period again of 2 pi. We go up, we have the parabola shape on the bottom, and then we're coming back down to our point at 1. So it takes 2 pi to complete one cycle. This time we have vertical asymptotes at pi over 2, 3 pi over 2, and so on. So we start at pi over 2, and every pi after that, we have a vertical asymptote. Again, we have no x-intercepts. But this time we do have a y-intercept at 0, 1. Domain, again, any x is okay as long as it's not one of our vertical asymptotes. And our range will end up being the same as cosecant. So we can either write it as y is greater than or equal to 1 and less than or equal to -1, or we can write that compound inequality. So last but not least, we have our cotangent function, which again, cotangent is 1 over tan. So we're looking for the reciprocal of the tan function. We'll start off by drawing our tan function. Tan of 0 was 0. Tan of pi over 4, and I'm realizing this scale isn't the best for this, but pi over 4 was 1. And then we had a vertical asymptote at pi over 2. Three pi over 4 is -1. Tan of pi is 0. Tan of 5 pi over 4 is 1. And we get another vertical asymptote at 3 pi over 2. And then we're at 7 pi over 4 is -1. And 2 pi, tan of 2 pi is 0. So our tan function looks like this. And now to draw our reciprocal. this is a step we haven't necessarily seen before. So first we have vertical asymptotes wherever we had an x-intercept. That we're used to. And now wherever we have a vertical asymptote in our original function, this one didn't show up very well. Where we had a vertical asymptote in our original function, that becomes an x-intercept in our new function. These vertical asymptotes are where the function's undefined, and the reciprocal of 1 over 0 or anything else that's undefined is 0. The points that were positive and negative 1 stay the same. And so when we draw this, we end up, it looks an awful lot like a reflected tan function. So our period for this function, similar to tan, we're completing one cycle every pi. We have a vertical asymptote every multiple of pi. We have x-intercepts at x equals pi over 2, and then every pi after that, pi over 2, 3 pi over 2, 5 pi over 2, and so on. There's no y-intercept. Domain, all x's except for where we have vertical asymptotes. And our range, similar to our tan function, our range is all y's in our. That's the graphs of cosecant, secant, and cotangent. We'll do a little bit more of those in the next few lessons, but that's the end of this one. If you have any questions, keep asking them, and have a good rest of your day. Bye.